Ingamana, ingareo, ro rakatirama. Tenakoto, tenakoto, tenakoto. Norera, ko waio, ko Harleen Hain, takoingawa, ko te tumuaki o te whariwanaka o atako aho. Namihi nui. Kia ora, tenakoto, tenakoto, tenatato katoa. Good evening, everyone. My name is Harleen Hain, and I have the great privilege of being the Vice Chancellor here at the University of Otago, and it is my great pleasure to warmly welcome each and every one of you to this inaugural professorial lecture for Professor Neil Waddell. On behalf of the university, I'd like to extend a particularly warm welcome to Neil's daughter, who is here with us tonight, and to his colleagues from the School of Dentistry. To all of you, Nomai, Haramai, welcome. I'd also like to acknowledge all of the staff and the students from around the University of Otago and members of the wider Dunedin community who have chosen to spend their valuable time with us. I'm sure that you will, like the rest of us, enjoy what Neil has to say. These lectures are a really important time of celebration for the University of Otago, and I'm so incredibly happy to see so many people here to share in the celebration of this amazing transition in Neil's career. Now, as you will learn from Neil's lecture this evening, he is an effective and motivating teacher, a popular postgraduate supervisor, and a very successful researcher. He's also provided exceptional service to his discipline, his program, his faculty, his university, and to his wider profession. So Neil, on behalf of the University of Otago, I would like to warmly congratulate you on your very well-earned promotion to professor. I am very much looking forward to your lecture this evening. I will now call on Professor Richard Cannon to tell us just a little bit more about Neil's journey to professor. Norera. Tenakoto, tenakoto, tenatato katoa.
Good evening. It's my pleasure to introduce today's speaker, Neil Waddell. Neil obtained a higher diploma of education from the University of Natal in South Africa, and then a master's diploma in dental technology, also from Natal. Neil worked as a lecturer and senior lecturer in dental technology in Natal, and subsequently worked as a technical advisor for Gunz Dental Supply Company. In the early 2000s, Neil came to Otago, where he gained a postgraduate diploma in clinical dental technology and a PhD in which he studied the cause of failure of implant-supported overdentures. And since then, he's risen through the ranks from senior teaching fellow through senior lecturer, associate professor, to a well-deserved professorship. You're probably familiar with the frontline oral health professionals, the dentists, the dental therapists, and the hygienists, but you may be less familiar with the important work that goes on behind the scenes by the dental technologists who make the dentures and other appliances, and the biomaterial scientists who develop and test new materials and technologies. Neil has made major contributions to both dental technology and biomaterial science at Otago. Neil has supervised 14 master's students and 22 doctoral students and attracted approximately $3 million in research funding. Neil introduced the highly successful annual Dental Technology Research Day in 2006 and is currently the director of the Biomechanics and Biomaterials Research Program in the Sir John Walsh Research Institute, Faculty of Dentistry, and he is head of the Discipline of Dental Biomaterials. Neil has expertise in the areas of implant overdentures, dental materials, maxillofacial and ocular prosthetics, and crown and bridge ceramic restorations. Neil conducts research in dental materials, cranio-facial biomechanics, including bite forces, prosthetic failure mechanisms, adhesion of dental materials, subconcussive brain injury research, in vitro modeling of blunt force trauma, forensic odontology, wounding and ballistic blood splatter analysis, and development of simulant materials for forensic modeling. The list goes on, and I'm sure Neil will touch on several of these areas this evening, and I'm looking forward very much to hearing Neil's presentation on oral microengineering. So please join me in welcoming Neil to the lectern.
Vice-Chancellor, thank you very much for those kind words. Richard, thank you very much for those kind words. And thank you very much, everyone, for coming tonight. And I'm hoping to give you a bit of a flavor of my journey here and my walk at the University of Otago. And my title, Oral Microengineering, to give you some insights into the engineering side of the biomechanics and biomaterials that we carry out to restore people's dentition. And towards the end, we'll switch focus and look at some of the subconcussive brain injury research just to change the flavor as such. So a little bit about myself. I was born in a country called Rhodesia in central southern Africa, way back in 1954, and in a town called Bulawayo. And a feature of that town is the very wide streets. And that top right-hand little image there is of an ox wagon, which was the form of transport in those days when the country was first formed in 1890. And you had to be able to do a U-turn with a span of oxen of 10 to 12 pairs in the street, hence the wide streets. So that's the town that I was born in. But I actually grew up most of my time in the capital city, which was called Salisbury then. And a feature again, the wide streets. But another feature was all the streets were lined with jacaranda trees. And at that time of the year, there was this glorious color of purple throughout the city. And as the little flowers would fall, we'd have then a mat of purple. And as you rode down the streets, you'd hear the little popping of the flowers as we were sort of heading into work. So on leaving school, I went and joined the army, the 1st Battalion Rhodesia Regiment. At the time, Rhodesia was fighting a war on two fronts. From Mozambique, Robert Mugabe's ZIPRA forces with North Korean trained and Communist Chinese trained and backed. And there was a war on that front. And on the northern front, we had Joshua Nkomo and his forces, and they were East German and Russian trained. So there was a war taking place at the time. And then in 1976, I did selection for the SAS. It was C Rhodesia Squadron 22 SAS Regiment. And the background to the SAS is that in the Second World War, a gentleman by the name of David Sterling formed the SAS, and they were the first sort of special forces where they went behind enemy lines and caused as much trouble as they could. And at the end of the war, although they were very successful, they were then disestablished. But when the Malayan campaign came along, the Commonwealth decided to resurrect the SAS. And New Zealand formed a squadron, which is our current New Zealand SAS, which they sent. Australia formed a squadron, which they sent, and they are still current today. And the British formed A, B, C, and D squadron. And C squadron was drawn from soldiers from Rhodesia. And so, as I say, I did selection. There was 120 of us started, and 6 of us made it that particular round. And for the rest of the years, until 1980, I played soldiers with the SAS. But in 1980, things changed. There was a political agreement to stop the war, and the country became Zimbabwe, and Robert Mugabe became the president. So I and a third of the squadron left within 6 weeks, and we were absorbed into one reconnaissance commando, which was the South African Special Forces equivalent unit, and they were based in Durban. And that's how I ended up in Durban in South Africa. But the novelty of playing soldiers had worn off pretty quickly, and a year later I left, and I went off and became a dental technician. And that's when life changed, and it was a different type of enjoyment in that. So in 1984, I was successful when I applied for a position to teach as a lecturer in the dental technology department at Technikon Natal. And they offered a 4-year higher diploma in dental technology. And the images you see there on the two right-hand side are some images of the laboratories where students would have a workstation each and would learn how to make teeth. And then in 1997, I and my family, and then you can see in the top left-hand side, the 3 children, we then immigrated from South Africa to New Zealand, and I was appointed as a senior lecturer at the Central Institute of Technology, where they had a 3-year diploma in dental technology, and I started teaching there. And the top little right-hand image shows you the teaching laboratories where we taught students, and the bottom one is an aerial view of the campus at the time. But much to my shock, within 3 weeks, the then CEO, Professor Michael Cooper, got us all together, the staff, and said, oh, by the way, the government is now going to disestablish CIT over the next couple of years. So anyway, I was offered a job in Australia, and the prospects were short-term at the CIT, and so we moved to Australia, where I was a technical advisor for a big Australian-based dental supply company, and we were based out of Sydney. And my time in the supply company industry was great, but I really missed academia. And I was very, very pleased when I was successful in my application to come back into the academic tertiary world again. And I was appointed as a senior teaching fellow to start the new Bachelor of Dental Technology degree that was just starting up here at Otago. So Professor Peter Innes, in his wisdom at the time, had seemed to incorporate or to bring under the umbrella of the faculty all the different components of the dental team, and we were the last members of the team to come into the faculty. And as Richard explained, the dental technicians are the unseen side of dentistry. We are the technical people who quietly make the teeth and the prostheses, etc., and have very little contact with patients apart from maybe taking color and shade of teeth, etc. And that was the start of my career. Professor Innes had put in place the Bachelor of Dental Technology and the postgraduate diploma in clinical dental technology. And then when I came on board and was head of the discipline, I then put in place the postgraduate diploma of dental technology, leading through to the master's degree in dental technology. And then later, my colleague John Arts put in place the honors Bachelor of Dental Technology with honors, and that has now given several pathways, and I'm pleased to say we have a very vibrant postgraduate program at all the different levels for our undergrads to then have options to go into. And this has paid dividends for our program, and many of the pictures I'll show you of staff and postgraduate students are actually graduates from those programs. And so here's a picture of one of the teaching labs in the Sir John Walsh, which is now been refurbished. And it always amuses me that we call them dental laboratories because they're actually manufacturing facilities. They don't look anything like a typical laboratory. Okay, so moving on. We talk about standing on the shoulders of giants. I need to acknowledge these three gentlemen who've been instrumental in my career in academia. Just 2 seconds. The first is Dr. Dirk Kutzer. He supervised me through my master's at Technikon Natal, and he was the one who passed on the passion for research. And I have a great debt of gratitude to him. And then when I did my PhD, the other two gentlemen, Professor Mike Swain and Professor Jules Kieser, had an immense influence on my understanding and my sort of school of thought and my thinking. Mike taught me the importance of understand the simple before you build the simple block on the simple block to get to the complex. Because if you haven't understood the basic simple component, you've got no chance of explaining the more complex. And Jules sadly has gone to his rest, but Jules was instrumental in opening up the understanding of working as part of a team, that several people bringing their expertise together can achieve far more than you can by yourself. And also, he was the master of networking, and I've tried to emulate some of that as my career has gone on. There's also three other gentlemen I want to really acknowledge that in the recent years, these three, Warwick Duncan, Darryl Tong, and Carl Lyons, have mentored me in my sort of time moving up through the ranks, and I really wish to thank them personally, a deep debt of gratitude to them for how they've helped me in my progression and sort of passing on their knowledge and tips. And I hope in some way to do the same for those who are coming up behind me. So the theme of what I'm going to be saying tonight is this working as part of a team. All of my publications are multiple author publications. I have not published once by myself. And what I've learned is that when a group of good people come together, you can achieve much. And so these are colleagues and past colleagues that I've put up on the screen. And I'm not going to name them all, but there's three I want to signal out, and that's the three at the bottom left there. our professional staff, without their support, I think things would grind to a halt in a nanosecond if we didn't have dedicated professional people. And I just want to name them. Bruce McLennan, he was a master of knowing where things were, who could do what, how you could get things done. And I'd need a little bit of something made for a jig or something like that. And in the early days, we didn't have much research funding at that stage. And I'd go to Bruce and say, who could make this device for me? And he would tell me that there's a little workshop there with someone there, and he just knew where everybody was. And he was an immense help to support us getting going in the early days like that. Liz Gervin, she, in my opinion, has an advanced pilot's license to fly, drive those scanning electron microscopes that are under her control. And a large part of the research that we have been involved in is involved electron microscopy. And Liz has been instrumental in us achieving results in that area. And then finally, Leo Van Rens, who's the instrument technician under the Linda Ferguson down in the dungeon in the basement there. His skill as an instrument maker and his knowledge and precision has enabled us. He produces world-class quality jigs, etc. And then what can I say? Without our postgraduates and our honors students, we wouldn't achieve a fraction of what we achieve. And so as I talk about what the research areas that I'm going to talk about tonight, please, it's always, I'm going to use the word we and our groups, etc., because it's all of us in the various groups that have managed to achieve the outcomes. So let's get into some research. Understanding bite forces is really important because it has huge implications for the materials we select and for the restorations we design. Your muscles of mastication are extremely powerful, and literally if you put your finger in the back of your mouth and give it a nip, you can do a lot of damage there, as Mike Tyson did to poor old, what's his name's ear there, Evander Holyfield. So we have a natural mechanism, and the good Lord above created us with this marvelous system called the proprioceptive nerve feedback from our teeth, so that when we bite down hard, each tooth sends a signal through the nerves back to the brain and says, listen, stop biting now, it's getting sore. And in that way, we don't overload our teeth. We don't smash them up, per se. And this is great because when we restore teeth, in this instance here, and they sit on a natural roots, there's a periodontal membrane which has got like a cushioning effect as well as the nerves. And so we don't tend to overload these teeth too much. But with the advent of implants that we've had over the last 20 plus years, in this instance here now, there's no nerve feedback because the nerves are gone, and the implant is osseointegrated into the bone, and so we don't have any cushioning effect here. And so while failures are not that common in the mouth, they do occur, and so we need to understand these bite forces and these mechanisms of failure if we want to then understand what caused them and avoid them going forward in the future. So one of our groups has been looking at this issue of contact point stresses on teeth and restorations. And if I read the title of the publication here, it's Maximum Voluntary Bite Force. And the voluntary is that pain feedback. So when you bite to the max, it tells you stop biting now. Occlusal contact points and associated stresses on posterior teeth. And I've used two words there, force and stress. And so what do we mean by this word force and stress? So we take the elephant on the right. It is a large mass, and force is defined by mass times acceleration. So as it trundles down the road, the mass, with the speed at which it puts its foot down, is distributed across the base of the pad of its foot, and that's the area to which it's subjected. And so stress is the force divided by the surface area to which it's applied. And conversely, the little deer, which is a fraction of the mass of the elephant, but when it trots down the same road, the size of its hooves is very small. And so now when you take the area to which the force is applied, it will produce a higher stress than the elephant, and it'll imprint into that. So in engineering terms, we use stress to look at the strength of materials. So what we did as a group is we, through much experimentation, I must say, developed this bite force transducer frame, and the experiments that went into finding the right metals and configurations was extensive. And to that we attach two strain gauges, which measure then electronically any distortion in the system. And once we had come up with the design, we then went to our universal testing machine where we could then apply forces to it and correlate that to the voltage output from the strain gauges, and then say, right, this output gives this amount of force. And I'm using the word force here. And once we had achieved that, we then cast or produced in metal the upper and lower teeth, which we then again put into our universal testing machine, where we could then put it into that and ensure that we were getting tooth-to-tooth contact, because we wanted to measure individual teeth and not a group of teeth. And having calibrated that, we went to clinical trial phase where we had a significant number of volunteers induced with a little card to New World. Thank you very much. But we were able now to measure the bite force on the individual teeth in the posterior of the mouth. And once we had done that, we then scanned using laser scanning technology, say, the upper and lower teeth, and this gives a three-dimensional output, and that allows us then in the computer as such to then calculate the surface areas of these contact points and contact areas. And once you know the force and once you know the area to which it's applied, you can calculate the stress. And of the 174 teeth that we measured, 21.8% were producing stresses above 1,200 megapascals. And the reason that that's a significant number is the strongest material that we use as an all-ceramic in restoring the mouth has a flexural strength of 1,200 megapascals, which is a stress value. So that's telling us that in terms of designing and selecting materials to go into the posterior or your back teeth, it's really important that we know what are the bite forces, stroke the stresses on the contact points, and we design and select accordingly. And this informs us in terms of our treatment planning and designing what we're going to do. So another area we looked at as a group was what is the influence of these forces on the teeth and various implant retention systems, and also on or flexibility of the mandible. So we came up with an in vitro simulation where we took the muscles of mastication as bungee cords, but we attached them to the right attachment points in the mouth. And if you look very carefully here, you'll see a load cell down here, and we could swing that in an arc to the different teeth. And in that way, when we raise the frame of the testing machine, the bungees would then lift a certain amount of force, and that would then be reflected on this output that you see over here. And we could then induce on an individual tooth an amount of bite force. And then attached to the mandible, we had a whole lot of strain gauges in all different places, allowing us to then measure the flexibility of the mandible, what was flexing where, as well as things like should we screw retain or cement retain. So up here you see these little screws going in, and there you can see the screw holes. And down here there's no screw holes. That's what we call cement retained. So when you screw something together, you have a thing called compliance. There's a certain amount of movement and give in the combination of the screws. But when you cement retain, it's rigid. And depending on the flexing of the mandible when you're loading it, you can then rupture that cement attachment or that cement bond, and that becomes the weak link in the system. So we were able to study this, as well as using very stiff materials like zirconia, which is very, very rigid, versus more ductile systems like dental alloys that you see on the right. So this combination of variables, we were enabled to then, using this in vitro approach, look at, do we cement retain, do we screw retain? Do we use metallic systems like you see here, or ceramic systems like you see here? And that enabled us to then inform that type of treatment planning. We not only look at closing forces, bite forces, but also jaw opening forces. And we have a group investigating this area led by Professor Brunton, and that helps to inform things like temporomandibular joint dysfunction, things like that. And so we have a group measuring that as well. So all aspects of the biomechanics of what's taking place in terms of mastication or your jaw and et cetera, we are, or have done, investigated that. So what about things going wrong. And one of the things we do is we look at how engineers do an analysis of failure, and we try to apply similar types of principles to failure in the mouth. And one of the areas we looked at was the failure of soldered bar attachment systems in implant overdentures. And what was happening at the time is we were running clinical trials on attachments to help stabilize these complete dentures. And in some cases we had ball attachments like this, and in others we had bars, and they were looking to see which were the most effective. But the problem was that some of these bars were failing at the solder joint after 1 or 2 years, and their lifespan should have been 10 to 12 years. And why were they failing? And here's another example of a similar sort of failure. And so here's a photograph of one of the failures, and I'm just going to alert you to this gray area here and the gray area here, and keep that in the back of your mind. We'll come back to that. So taking the failed bars and components off to the scanning electron microscope, we're having a very close look. It was very interesting. We saw extensive corrosion, the solder joints being undermined by corrosion, as well as corrosion attacking the gold cylinder. This is a non-oxidizing gold cylinder of pure platinum, palladium, and gold. And from this, defects were being induced, and we were seeing stress corrosion cracking. And this appeared to be the initiation of failure of these joints. We also observed in some failures fatigue failure, and we were able to establish that by these little striations you see here, which are signs of fatigue. Every time you bite and you open up, bite and you open up, you leave behind a little line, a bit like the rings on a tree when you age a tree. So we modeled that using a mathematical model to look at the different designs in terms of a rounded sort of connection or a straight connection, and as well as looking at the internal types of stresses. And this sort of helped us focus or imagine where these stresses would be focused. Was it to do with design or materials? And it helps to then start to understand on a bigger picture of where the stresses are focused and where the potential causes could be. And what was also interesting, we found inside these failed cylinders, corrosion caused by crevice corrosion. So some of these stresses you see here, in actual fact, the failure had been initiated inside the implant from corrosion as well as on the outside. So running parallel to this, the group took some original components, a bar that you see over here, and a gold cylinder, and a solder here. And this is shown as a bar there, the solder, and the gold cylinders down here. And we then soldered them together, polished them up, went to the scanning electron microscope, and at the same time, we took them and nano-indented them. These little indents you see running here allow us to measure the modulus of elasticity, which is stiffness, and the hardness of the various components across the joint. And what we found was that just inside the edge of the cylinder was a gray zone that we observed, and when we looked at its hardness and modulus, it was significantly higher than the rest of the components of the system. And this was quite interesting. So running parallel to that, we said, well, let's fatigue cycle these. You know, in the aircraft industry, when a plane falls out the sky, they will often do these types of tests. And so we ran 2 in a dry environment and 2 in a wet, corrosive environment, and we cycled these until they failed. And at different stages, we were able to take them out, look at under the microscope, see the progress of what was taking place, until we got failure of the solder joint. And once they failed, we then embedded them and again cut them through. So we cut them lengthwise like this, and then polished them up to look under the microscope. And what was interesting was that this gray zone here has got the crack in it. So what we found was the cracks were initiating in the solder, often through corrosion, but once they reached the cylinder, it would be a rapid propagation down that through this gray zone. And the question was, what is it about this zone that is causing the crack to, in a catastrophic way, propagate down? So we made up beams, and in the beam we incorporate some of the non-oxidizing gold cylinder on one side and the solder on the other, and this is what we call a fracture toughness test. So we notch it here to induce the crack to the direction and the area we want the crack to occur in. We load it in a 3-point bend, and then once we break it, we are able to calculate the fracture toughness. And sure enough, the Surface topography showed us a brittle mode type failure, so it was brittle as opposed to ductile, we'd expect to see in a metal. And we found the fracture toughness was the same as that of zirconia. So inadvertently, this soldering process was creating a ceramic-like brittle zone within a ductile metal system. And once a crack reached it, there was a catastrophic failure. And this was confirmed when we did the elemental analysis using EDS. And what we were finding was that when the solder was soldered to the bar, which was a type 4 gold alloy, they contained similar elements and there was equilibrium. There was no movement. But when it was soldered to the non-oxidizing gold cylinder, platinum and palladium are very reactive, especially at temperature. And the gold, platinum, palladium was migrating out, diffusing out into the solder, and copper, zinc, and silver was migrating inwards, forming this gray zone. And this was this brittle zone that we were inadvertently creating. So we came up with a solution to the problem. Don't use non-oxidizing gold cylinders to solder bar attachment systems. You instead order the plastic one, and you place a sprue onto the plastic, which you then burn out in a furnace and cast it through a casting process. And then you go ahead and solder your gold bars to your gold cylinders, which are now being cast. And you keep the preformed non-oxidizing gold cylinders for laser welding type situations where you don't have long heat exposure or thermal cycles. Now, when we sort of found the answer to that problem, new problems were arising. And this was a chipping or failure of the bond of porcelain to zirconia substructures, and at the same time to cobalt chrome, which is a metal substructure. So what was happening was that the industry had been promoting the use of zirconia as a new material with CAD-CAM type manufacturing processes. And worldwide, reports were coming in that the porcelain was chipping off. At the same time, the gold price, the precious metal price, had gone skyrocketing up through the roof, and the whole world was switching away from noble-based alloys to cobalt chrome. And likewise, we were doing the same here. And we were finding problems with the veneering porcelains chipping away from it. So before I go into more detail on that, let's try and give you an insight as to how we veneer porcelain to these substructures. So up here is a metal framework that we wax up and cast. Now that could be metal or it could be a ceramic like zirconia. It's just the framework. And then at each stage we put a layer of porcelains on, which we then fire in one of these furnaces to 930 degrees centigrade. And there's a series of firings as we go through because the porcelain shrinks when we put it on, and it can have up to sort of 8 firings depending on the size of the restoration. So just to show you an example, here's a case where you have a central, a lateral, and a canine, i.e. your 2 front teeth and the one next to it and your canine. There's the all-ceramic zirconia substructure being tried in the mouth. Back on the cast, the dental technician now going to make it. That's the first layer has been fired on. And then we start to layer these porcelains, which are powder mixed with a liquid, and we take a paintbrush, and we start to build up the different colors and translucencies. It's like painting with glass. And this is slowly built up until we get the shapes and the nuances of color in the right places. And once it then reaches the size we want, we slightly overbuild it because of the shrinkage. Then we take it to the furnace and we fire it. It'll shrink. As you see, it's shrunk down, and then we'll put the next layer on. And again, when we get it to the shape we want, we fire that again. And this is what you see if the job has been well done. And there's your central, your lateral, and your canine. So some very beautiful work by a dental ceramist in that case. Now, this next little video is very short, but it'll give you an insight as to how we build these crowns. And it's from a manufacturing publicity web. And you'll notice on the side here the different types of teeth. And we can make old teeth, young teeth, ugly teeth, beautiful teeth. Once we know what the patient's teeth look like, we can match it by layering in these different layers of porcelains and enamels and translucents and colors. And so what's showing you here in 50 seconds, in actual fact, would take probably an hour and a half to 2 hours for a ceramist to make one of these teeth. And at each stage, each of these will have had at least 5 if not more firings, a thermal cycle through one of those porcelain furnaces. So this porcelain was chipping off, and patients aren't happy when the beautiful teeth they have start to fail. So we put the word out to the dentists in New Zealand and said, please, if you've got one of these zirconia veneered situations, please send it to us that we can do an analysis of failure. And Dr. Erin Collins up in Auckland very kindly sent us this one. And here you can just see the chip on this little edge here. And that's it coated, ready to go into the electron microscope. We also did a micro CT scan on it. And this here shows you the surface. And using fractography, which is a science in itself, we can track back from the different areas to the source of the failure, and we're even able to sort of calculate the sort of forces involved in initiating that failure. And the first thing that we sort of realized as the group looked at this, and that was that the thermal conductivity, that's the rate at which heat is transferred through a material, of the veneering porcelains here was very similar to the zirconia. And that has huge implications to the cooling when it comes out of the furnace. If you look at metals, 315 compared to that, they will lose the heat at a much more rapid rate. And likewise, you see the aluminium oxides. And the implications of this is that when the crown comes out of the furnace, it's losing the heat through the, in the case of a metal, from the inside to the outside. So as it's contracting and cooling, it goes from a liquid, because the porcelain is got to be fired and enameled, to a solid. It's solidifying from the inside out. But in the case of the zirconia, it's losing heat equally, both from the outside and the inside. And the result of that is that if you fast cool it, and all the manufacturers had a fast cooling cycle as part of their recommended procedure, what happens is the porcelain in the middle, which is still liquid, now cannot contract, and it sets up an area of tension inside the porcelain. And this was the cause of the cracking or the chipping that was taking place. And to validate that, we took tablets of porcelain and we put thermocouples, one in the center and one on the outside, and we heated it up until the two were now at the same temperature, and this was above the glass transition of the porcelain. And then we cooled them at different rates. And when we cooled it quickly, this little area in the middle here is the glass transition. You can see that the outside reaches the glass transition before the inside, and that sets up this residual stress of tension in the middle of the porcelain. But when we cooled it slowly, we didn't get that situation, and you don't get the residual stress. And we moved to publish this very quickly because this was still a worldwide problem. And Otago was instrumental in the manufacturers worldwide changing their firing cycles to include a slow cool cycle on the last thermal cycle of the firing of the porcelains when you veneer it. And the manufacturers were very grateful to us because dentistry was about to walk away from zirconia because of these failures. And we were able to say, listen, here's the solution to the problem. You can keep using it. Now, in all research, you think you're solving one question, but you come up with another 4 or 5 questions that, well, what about this and what about that? And one of the questions was, what is the influence of the thickness of the porcelain that we're veneering in terms of the cooling cycles on the residual stresses? And as I said, we were using cobalt chrome and we were using all ceramics, and that's why I've shown here's a metal substructure and there's an all ceramic substructure. So looking at the all ceramic, we use indentation. So we take this little Vickers diamond, it's got a set shape, and we indent it into the surface of the porcelain, and you see these little cracks. And when you have a situation of no residual stress underneath the area you've cracked, the cracks have nothing to inhibit it, so they extend further. But if underneath that area you're indenting, there is tension in the underlying porcelain, it's trying to hold it together. It's a bit like a reinforced windscreen, toughened windscreen. Then the cracks are inhibited from extending. And there's a formula that we then use to convert that to residual stress. And then using a matrix like this, we were able to build different thicknesses of porcelain and then fire them, then go and indent them at different places that you see here, and then able to report the influence of do you veneer it too thick or too thin? What's the repercussions of that? And so, again, it informs us in terms of how we produce crowns and design their substructures. Coming to the cobalt chrome side, what we were seeing was a failure at the porcelain to metal interface where porcelain was breaking away. And what we found was that when we used electron backscatter diffraction to look at what was going on at the surfaces, what you see here is a 0.5 of a millimeter and a 1 millimeter thickness. So this area here would be that thickness. And we then placed porcelain on top of it. The little green area you see at the top is the porcelain, and that represents this area here. So there's your porcelain on top of the metal. And we then fired it and fired it and fired it, simulating when the crown is being first firing, second firing, etc. And we found that the phases were changing, and it was starting to form this phase at the top, which had different mechanical properties and was very rigid. So when the bilayer of the porcelain and the metal are contracting together, it was setting up these residual stresses. And this was quite serious. But at the same time, the manufacturers were launching different technologies, i.e. powder metallurgy and CAD-CAM mold, also in cobalt chrome. And our research then looking at that showed us that with these types of approaches, we were not getting that secondary phase forming on the multiple firings. And I'm pleased to say this informed the school when we then purchased our CAD-CAM milling system, and all of our substructures are now produced with the powder metallurgy component. Okay, let's change focus. If we keep going with teeth, it may become a little bit boring. So research involved in subconcussive brain injury using a forensic head model. One of the things as dental technicians is that we have that ability to make molds, use different materials, and we're always trying to make prostheses. These are a couple of cases that I've done in the past just to illustrate this ability to use simulant materials to replace lost structures, etc. So how did a bunch of dentists and dental technicians get involved in research on subconcussive brain injury? We need to track back a little bit in the story. We were asked to develop a skin skull brain model for forensic ballistic testing. And how this came about, Jules had an extensive network and had an active research, forensic research group running. And Dr. Michael Taylor, who is an international blood spatter expert, and he is a scientist with the ESR, so when the police have a homicide, they call in Dr. Taylor as the forensic scientist to do the investigation. And his colleague, Kevin Walsh, who was the ballistics expert, they asked us to make a skin skull brain model that they could then do research on that. Now, the other members of the team, Daryl and Warwick and Jules, you'll see the black here, and myself, had a military background, and so we immediately knew what it was about and were able to then bring our knowledge and expertise as well. We invited in Professor Mark Jeremy, who was an expert in fluid dynamics from the University of Canterbury Mechanical Engineering, and of course Mike Swain as our physicist. And one of the things that Jules had observed in these forensic call-outs that he was having to do, and by the way, there's many of our colleagues at the school who are part of the DVI team, Disaster Victim Identification, who get called in to help with the investigation or the analysis of these situations. And so we were well placed to sort of look at this. So how do we have rupturing of the skin from blunt force trauma? Now, the next little clip I'm going to show you, one of our postgrads did this without our permission. We didn't know she was going to do it. But when you see her, she's going to punch herself, but look at the area from the punch and the shock wave that moves out from that. That's quite important to understand that. If she'd asked us, we'd have said no, but it's very revealing in the same time. And this was in front of the high-speed camera. So using silicone as a skin and a sponge, we were then able to impact this. And while it is dry, there's no fluid in the sponge. You can impact it as many times as you want. Nothing changes. It elastically recovers fully. The moment you hydrate the sponge, you get a totally different reaction. The hydrostatic pressures are such that as you impact it, it cannot escape. And what happens then is the underlying tissue ruptures and the skin ruptures. And effectively, it's rupturing from the inside outwards because of the hydrostatic pressures from the blunt force trauma. And we were able to correlate this with post-mortem evidence. And again, let's say we were successful in publishing this. And from this, Dr. Mike Taylor, who was doing all of this research on blood spatter, immediately said, well, can we make this? Can we make that? And so we made up a fist for him. And here he is using the fist. And what they do is they then study how the blood moves, what direction it goes in, and they're able to do a whole lot of calculations from that. We even made a stabbing device for him to study that. There it is in the molds, etc. And so he's now able to attach this to a drop swing device where he can have repeatability and take the various measurements that he needs to do for the biomechanics, and then study the effects of that on a repeatable in vitro basis, etc. So the area that he was really interested in was this issue of ballistic impact to the head and the backspatter from that. And what they find at scenes is that if someone has shot themselves, there will always be tissue on the hand and tissue on the weapon. And if they go to investigate what potentially is a suicide and they don't find any backspatter on the hand, that implies the gun was planted. And what was potentially suicide now becomes a homicide investigation. And likewise, if it's not on the gun, then where is the weapon that did it? It's sort of disappeared. And so using our dental skills, molding skills, we then created a basic skin skull brain. And this shows you a bullet impacting it. That was our first prototype. We found that the resins we were using, which was the same resins we used for the mandible, which have the same mechanical properties as bone, were showing correct results. But our design didn't include the cerebral spinal fluid, and it didn't have the hydrated tissue component. So we readjusted our model to incorporate that using glycerol as the liquid, which we could then pigment with a color. And the next one I'm going to show you is a little movie, but it's a transparent movie, so it's not encased inside the skull per se, or the resin skull, but it illustrates what we're trying to investigate. So a bullet will come in from the right, and immediately you'll see ejection of tissue matter in the direction that it's come. And then you see the temporary cavity is formed, and now as it starts to collapse, you'll see a further ejection of blood and tissue matter in the direction that the bullet came. And this is what causes this back spatter that they find on the hand and on the gun. And so it was to investigate this that it was so important that we made this for Dr. Mike Taylor to do his investigations. Now, resulting from this, the Defence Academy in the United Kingdom picked up on this model that we had produced and said, well, could we come across and give it to them? And so we went across, and all four of Jules, Daryl, Warwick, and myself have been across there at different times. And we've been instrumental in helping them design helmet systems using our model. And here's a cool little photograph of Warwick standing with Deborah Carr. Deborah formerly was here at Otago as an engineer with textiles, and she worked for the Impact and Armor Group at the Defence Academy. So when all of this came to an end, we said, okay, let's change the focus. Daryl was very involved in the subconcussion side, and we said, okay, let's change the focus, use this knowledge we've built up with our simulant model, and direct it more at subconcussion. So definition, complex of concussion, that is, a complex pathophysiological process affecting the brain induced by traumatic biomechanical factors. And our interest is in the biomechanics side of it. And we've all seen these sickening images of sportsmen being injured in the field. But the problem was that when they don't show symptoms of concussion, it's subconcussion, it's below the threshold, they keep playing. And so we don't know much about it. This carry-on mentality is a problem. The injuries, we believe, are now cumulative, and evidence is now coming out that it is the case. And we're starting to see the long-term effects. And so we wanted to know, could we study this, find out what are the harmful thresholds, what is it that we could set up safe to study, and can we measure it in a safe way? And animal models are not appropriate because the anatomy is totally different, and in vivo studies are not really appropriate either. We don't go around and bang each other on the head with a hammer or whatever it might be. That's not quite right either. So we commenced the process, and we said, okay, well, what are the mechanical properties of the scalp? And one of our first BDS honours students, Nick Pittar, his project was to now run around the dental school and find as many victims as he could and use this little device called a gyrometer and measure the shore hardness on various places on their scalp. And sorry, just to go back to that, we correlated this with different elastomers, and our medium-bodied polyvinyl siloxane happens to have a similar mechanical property as that of the mean values of the scalp. And we further took these different silicones that we have, and we subjected them to continuous impact, because the model had to be able to withstand repeatable use, whereas if you hit someone on the head, on their skin, it injures first time. You don't keep hitting the same place. But our model, we couldn't keep building a new model every time. And so we then tested the properties, and again, we found that our, where's my mouse here? Here we go. The medium-bodied polyvinyl siloxane was similar to, in this case, pigskin, which we had just gone down to New World and got some of. And again, we were able to then publish the outcomes. This then led to, well, what impact force should we use? And lo and behold, we had a significant number, about 10 practitioners of the sport of kendo in the school at the time. And Daryl was the black belt leader of the group. And you may have wondered why Daryl's got no hair on his head. I speculate that his hair follicles have given up on the number of impacts he's taken to his head over time, hence the lack of hair per se. Anyway, Leo van Rens built us this device. So it's got a quartz sensor here. It's got a beam that then triggers the recording as the sword comes down, time 1, time 2 for velocity. And we set this up in the passageway because we needed a high ceiling height, which wasn't available in the lab, and had a whole succession of staff and students who were all in the kendo club come along and beat the hell out of this device. And we then put some skin on top and some material they use on the kendo helmet. And this allowed us to establish these impact forces that were measurable, which we could then transfer across to our model. And once again, using our dental techniques of moldings, etc., we first of all made a simple prototype. And into that, we incorporated piezoelectric strips to record the impacts at the different layers: on top of the skin, under the skin, top of the skull, under the skull, top of brain, middle brain, base of brain, etc. And believe it or not, inside there is the head model, and we were then able to impact it and on top of the helmet. And we decided, yes, we were on the right track, but our recording data capture needed to be changed. The next phase was to a full anatomical model, and we duplicated a human skull and then incorporated into the various layers that I've just described accelerometers to be able to capture what was taking place when impacted. And there's the brain going in and then the top going on. And this then resulted in this model where we were able to then, with a drop rail, have the same amount of impact force as we had achieved. So we took our kendo impact device, put it under here, and then adjusted the height until we were achieving the same level. So we knew that we had that the same. And then we put the head, and you see this line here. That was the cerebral spinal fluid going in to maintain the pressure. And we then started to impact the model. And this allowed us then to measure these. And with this data capture device now, we were then able to measure at the different points what was taking place and look at the force transfer down through the various layers as well as the lateral movements as well. And the result of this research, we were able to then publish in the Journal of Concussion the effects of this. And this research is now ongoing. 2 secs. And we want to now continue with this to take it further. Excuse me. So where to from here? More topics, more funding, and more fun, okay? I feel privileged that I've been able to work with such great colleagues in such great groups on the wide variety of topics and projects that we've done. I really want to thank you all for including me in your groups and becoming part of my groups, etc. It's a great place to work, and thank you very much indeed. Much appreciated.
Neil, it really is a great pleasure for me to have this opportunity to thank you for your IPL tonight. We've known each other a long time and have become good friends from the day that you started through to now. And it really is fantastic for me to have the opportunity to stand up here in front of you to thank Neil for his presentation tonight. It was fascinating to hear of your journey from Bulawayo through to Dunedin, from the SAS, which we know little about for various reasons, I think, through to dental technology in Durban and eventually to Dunedin. It's ironic that the institute that drew you to New Zealand, CIT, and its closure is probably what created the opportunity for you to end up with us at Otago, and so for that I thank the Minister for doing that back in the 90s. Mike Swain, teaching you the importance of understanding the simple is exactly what you try to do with everyone that you work with, particularly your students. And for that, they really appreciate you and what you contribute. And also, I agree completely with you that with a group you can achieve much. But even in a group, you need people that can do research. And Neil, without you, the research couldn't happen. You've shown us some outstanding examples of your research and your contribution to the areas that you've done research in over the years, in areas including bite force investigations, stress corrosion with dental implants, the ballistic brain injuries, creation of the skull, skin-skull brain model, and studies into concussion and subconcussion. You really have made a significant contribution to research in your area, as well as to teaching in the university, to your profession, our profession, and to the university. And for that, I congratulate you on your promotion to Professor, and thank you for your IPL tonight. Thank you, Neil. And I have... a significant token of appreciation from the university, which when you hang it up, wherever it is you hang it up, you will look at it with pride every time you see it. So thank you, Neil.
Thank you very much. Thank you. Thank
you. Kia ora, tēnā tātou koutou. My name is Paul Brunton. I have the privilege to be the Pro-Vice Chancellor of Health Sciences. And my role tonight is to thank you, the audience, for coming to this event. The IPLs are a fantastic part of something that the university does, and they work extraordinarily well when they're well attended. So thank you very much for coming tonight. Your attendance here is very much appreciated. And it falls to me to invite you to join us for refreshments on the ground floor of the staff club. And if you follow the academic party, you'll find your way. But before we do that, I think we should thank Professor Waddell for an extraordinary lecture here tonight. Thank you.